Okay, this is from problem number 11, and I'm going to go through this problem in sort of the old-fashioned way, but there's actually a shortcut that I can show you in the FE material. But anyway, it's from problem 11 in your final. I guess I gave you some like a pre-final. So go ahead and look at the text for that and stop this video if you need to do that. But basically what you have is you have a tank, and this tank, this tank is 20 meters, has a 20-meter distance from the top surface of the tank to where there's an orifice that is 25 millimeters in diameter. And what it says in the problem is the exit here has a rounded edge, and the question is, what is the head loss? Okay, head loss through the orifice if it has a rounded entrance. Okay, so the first thing that I would say to myself is that I'm looking for basically an H value, a head loss due to friction of essentially, you can say this is a fitting, this exit, but this is going to be in terms of meters. So now what do I know? Well, I know that if I look at this situation, I know that the pressure at the out here is going to be atmospheric pressure, and I know that it's discharging to the atmosphere. So these are kind of two things that I know, and I also know that I can define some sort of XYZ coordinate system, YX, and if I call this 0 right here, then I know that the height, y or z, maybe I should call this z, I know that this height for this situation, let's call this point 2, let's call this point 1, I know that point 2, the z at point 2 is equal to 0. Now this is point 1, and I know that as soon as this starts discharging, this surface is going to drop, but the velocity at which it drops, just given the difference in size, the velocity is essentially 0 compared to the discharge velocity down here. So velocity 1 is about 0. So when I of course what I'm going to do is apply the Bernoulli equation to this thing. I know that I have water that is dropping through a gravitational potential field, and it's discharging out here. It's gaining kinetic energy here at the orifice. And what I'm going to do is look at basically the energy at point 1 and the energy at point 2 through the Bernoulli relationship with the friction added in. So hold on a sec here. I'm going to go to my FE. How do I do that? Oh, I think I just click here. So I have, here we go. So this is the area from the fundamentals reference material. It's under minor losses, pipes, fittings, and contractions. I'm going to use this equation down here, and note that the fitting loss is basically equal to 1 velocity head, v squared over 2g, times some value c. Now if you scroll down in this the FE reference material, you can see these different kinds of head loss situations, and you could see that the value of c for a rounded entrance is on the order of 0.1. That's the situation right here. Now the shortcut is actually all embedded in this diagram over here, that this is essentially jet propulsion, where you have a fluid discharging to an open atmosphere, and it just tells you that from this distance, the V2 is equal to root 2gh. So you can just cut to the chase and use the velocity 2 here equal to root 2g times the h, and then look at what the head loss is through that orifice. But I'm going to do this the old-fashioned way. So anyway, back to this equation. Let's go to here. I'll write down this equation. So I have P1 over rho g plus v1 squared over 2g plus z1 equals p2 over rho g plus v2 squared over 2g plus z2 plus hf, this is the head loss from friction in pipes really, and hf for fitting. Again, we're kind of approximating this for this case. Now, there's a number of things that we can cancel because of our choices. So we chose that the z of 0 here, so that makes the z2 0. This z1 then becomes our 20 meters. Now, the pressures are the same, atmosphere here, atmosphere here. That drops this term out because it's the same on both sides. We've already said that the V1 is 0, so that drops that term out. Now, the HF is for frictional loss in pipes. We don't really have a pipe. We're going to drop that term out as well. So we just have this term, and we know from the FE material that is equal to, that HF can be rewritten as C times V2 squared over 2G. And the C value is 0.1. So if I rewrite my equation, I know I have 20 meters is equal to 1 head loss here, oops, eraser, head loss here plus 0.1 head loss, so it's 1.1 V2 squared over 2G. Now, like I said, we could directly get V from the jet propulsion equal to root 2G H, that equation, or we can solve for V here, and you could see it's basically root 2GH, but oh, I see. No, that in that jet propulsion one, it was neglecting friction, so I'm glad we're doing this the old-fashioned way. So let's bring this over, and I'll go to the next page. We've got 20 meters times 2G divided by 1.1 is equal to V2 squared. So we've got that V2 is equal to the square root of 20 meters times 2 times 9.8 meters per second squared divided by 1.1. Okay, approximations here. I'm totally approximating, so I'm going to say this is 20. This is like 20. 2 times 9.8, that's like 2 times 10, that's 20, 10 times 20. I'm going to say that the square root of this is about 20. 20 meters per second is the velocity V2. But what were we asking about? We were asking about the head loss. So the head loss, we recall, is from the fitting, in this case, is simply equal to C times V squared over 2G. Gosh, we could have done something simpler, maybe. This would have been easier. So we could have said that basically the head loss was, if I rearrange this, 20 meters over 1. Could we have done that? Oh, no. Anyway, ignore that. So we've got HF fitting is equal to 0.1 times 20 squared over 2G, 20 meters per second. I'm kind of cheating because I'm not using the units. I really should. Meters squared per second squared divided by meters per second squared. I'm looking at these units. That's going to give me meters. That's exactly what I want. So I'm going to say that HF of the fitting is 0.1 times 20 divided by 2 is 10 over G is about, really that's about 1. It's a little more than 1. Squared, well, times 0.1 times 1 squared. We're going to call that 0.1. That is kind of, if you're using a calculator, that's probably like 0.12. Just approximate. This is how to solve the problem.